I'm definitely excited to be talking here because so this is actually my first PyData, and I also went to my first PyCon this year. So the drug addiction has been started, so that would be a good thing. And I packed some stuff in here, and I want to be conscious of time, so I apologize if I talk quickly. You could feel free to interrupt with questions, but just to give you an idea of the pace of the talk. In this little set here, the first element of the array is who I am, the second one is what I do, the third one is where I do it, and the fourth one is the best place to get in contact with me. So I do work at Context Relevant now. It's a machine learning and distributed compute company in Seattle, but almost all of what I'm going to talk about today was done while I was an employee here at Microsoft, actually. So what do you need to know about me? What's actually sort of more important, what you need to know about me is what I am not, right? So I'm a data scientist. I'm not a production programmer. And anyone who's done a code review with me will contest that is definitely true. But I'm getting better. Don't you worry. But that's who I am. And I work a lot, though, with developers, right? So if this is me, who is them? Them as developers, these are real programmers, right? People that know what malloc is and people that have lunchtime discussions about Haskell and Python generators and love the yield from abilities in Python 3, all of these things. And the problem, though, is that when you want to build an experimentation platform, you need both of these people. I'm definitely of the opinion that when data scientists and developers work together, they can create something that's better than either of them can create on their own. And actually, that's what I did for about a year at Microsoft, is I work on building a large-scale experimentation platform, right? So when I say large-scale, I do really mean large-scale, like tens of millions of users with 100 millions of requests every day. And there are certain things that go on when you start to scale at that size. But perhaps the most important thing that happened is we couldn't really communicate when we first started building the experimentation platform. So data scientists say, this is how you do randomized controlled trials or experimentation or A/B testing. This is what you want to call it. And a lot of the developers were like, OK, I have no idea what that is. And all of this code you wrote is trash because I can't run it for 100,000 users, let alone 10 million users. So there's a lot of tension about well, how do we resolve these differences, right? And it actually sort of organically came about that writing unit tests and communicating with each other in unit testing was a great way to do that. Because everybody understands whether or not a test passes, right? If the code runs, no assertion errors, your test passes, everything is good. So a data scientist can then write unit tests that the developers can work with and go back and forth about. And once all of those tests pass, you have sort of this robust, magically, of course, you have this robust experimentation system that gets you exactly what you need, right? So it's reducing the task of building this abstract thing called an experimentation system to writing a set of unit tests, the passes of which result in the product you want, right? It's not that crazy, right? That is test-driven development. So I'm not like a hardcore TDD person, though, so no pitchforks and torches or anything like that. But normally when I talk about these kind of things, hopefully I will prove this to you, that unit testing is useful for this in the next 30 minutes or so. But normally when I talk about experimentation, I just assume this is something that everyone does all the time, and everyone does A/B testing, and everybody has products that are consumer facing. So I always skip over this, and that is the biggest mistake I make on almost all of these talks, right? So for just 1 second, I want to expose a lot of my biases about what I think experimentation is and why we need it. And specific what I mean when I say experimentation, right? So there's a question of who needs experimentation, and obviously I'm of the opinion that we do. And when I say we, though, I mean we in humans, right? So it's not actually too overly dramatic to say that most of the scientific truths we know from experimental lab science have come about because of hypothesis testing. Right? So we know aspirin helps with heart attacks because someone did a randomized controlled trial of that. So if you go to the emergency room and you complain of heart pain, before they even take you back there, they give you 2 aspirin because they know that works. And they know it because of controlled trials. So how do we know the Higgs boson likely exists, right? You probably read some popular articles about how the Large Hadron Collider got a 6 sigma result. What does that mean? Null hypothesis was something, aka Higgs boson doesn't exist. The result we got was 6 standard deviations away from the mean of that null hypothesis. That is how we know it exists. So this is how we collectively decide what is true. And the canonical example we always have of why people should have done this but didn't in the past is bloodletting. So back in the day, if you got sick, they thought it was something inside of your blood, so people's blood would be let. This is one of the few known photos, false color obviously, of someone having their blood let out. And you see a lot of times people say, oh, we need experimentation because people did dumb things like this, right? Well, that's not the only reason you need it, all right? It's not only to sort of help us not make mistakes. Mistakes are fine. Anyone who's written code and never made a mistake is probably lying to you. So I actually think there's a better reason to say why we need experimentation. And it came when I was reading this book called Stiff by Roach. And She has, like, first off, you should read this book. It's amazing. It's sort of like a Bill Bryson, like, popular science exposition of cadavers and, like, what we use them for and all of these things. And she has a chapter in there that's very insightful, and it's about, like, medicinal uses of various cadavers. So that's all I'll say on that. You can read the book for the rest of it. But, you know, it's pretty common, most people understand it, that, you know, in varying cultures around the world for true and not so true reasons, people believe in the medicinal uses of lots of things, right? So a crushed rhinoceros horn will help you do this, or it was believed back in feudal times that, like, the saliva of the king would heal all of your wounds and stuff like that, right? So this falls into the category of stuff where you're like, well, I'm not sure if that's true or not, and you can come up with a number of ridiculous examples of why people shouldn't have done this and why they should have been smarter. But the interesting thing about that is, had people not been mucking around with this, we likely would have been much slower to realize that adrenaline exists and is useful, epinephrine, right? So if anyone here is extremely allergic to something or anyone has asthma attacks, you will understand that adrenaline and epinephrine save your life. And we learned this because people were mucking around with it, but they weren't very scientific about it. So the whole point of experimentation is to provide you with a way to muck around in very creative and free ways, but do so with guardrails that let you know when you're doing something that is worth it, that is true, and when you're doing something that is not going to be worth it and that is false. So I think of experimentation much less of a slap on the wrist for, you know, being unintelligent about the way you go about things, and more of it's a way that allows you to be creative without necessarily making as many mistakes as you would have before. A quick side note on that adrenaline thing, because it's just absolutely hilarious. The way they've actually figured out that adrenaline helps with asthma attacks is somebody noticed, a doctor, well, doctor in quote marks, this is way back in the day, a doctor noticed that when someone was having an asthma attack, if he scared the bejesus out of them, it stopped their asthma attack right away. So you can imagine, like, these early experiments where, like, he would induce asthma attacks in people and then, like, send them down a dark hallway and just jump out and scare the crap out of them. And, you know, that's how we started. So the idea is, like, maybe there's a better system to figure out whether or not adrenaline is a useful thing than that. So what do I mean when I say experimentation in the context of technology? You probably have all seen a diagram like this, and lucky for you, I drew my own, so it's an original piece of art. What do? You take users, you randomly split them into two groups. One of them will show you old, boring site that you have right now, and someone hired you to do things to change it into a sweet site that has, it's social, it's local, it's mobile, it's all these kinds of things. It's way better. And then you smash these two experiences together and do some stats, and then out the other side comes an experimental result, and that result tells you that your sweet site was better. And don't pretend like you don't have that bias that you think all of your changes are always going to be positive scorecards, because I know you do. And then, great, you get the front page of Hacker News, and everyone's happy. And this, like, conceptually at a high level, like, it is true, right? But I worked with the experimentation platform here at Bing, which is amazing, for just over a year. And then I set out to build my own. And real experimentation systems are actually more like this. So when you scale up to really big ones, they have tons of stuff going on inside. So when you want to run 3,000 experiments a week on over 100 million people, in which every user is in a number of experiments and 99% of them are being run in concurrent experiments at all at the same time, you end up getting something that's just very complicated. It's hard to actually tell what's going on. And so my whole point is that when you approach the building of this, you better know this machine works. So you can add all of these bells and whistles that do things you think are useful, but unless you know it works, you're going to be in big trouble. And I say you because it's always your fault, right? If you're in charge of the experimentation platform, my feature does work, the scorecard is wrong, your system is wrong, all of these kinds of things. So you need to guard yourself against that. And this actually leads me to my point of confusion, because, like, I really believe in experimentation, obviously, but then I can read things like this, right? So this is a headline from a blog post that said, "How Optimize, which is a third-party, very popular website, A/B testing company, almost got me fired." Right? So this person has a little bit of a grudge against the A/B testing. What happened here is that this person began to run a bunch of AA tests, which is where you run a normal experiment, but you show the same thing in both arms. And they were getting back significant result after significant result after significant result. This caused them to lose a lot of faith in their experimentation platform. So much so that they publicly called out another company to do this. There's another one, how AA testing, how I increased my conversions to 300% by doing absolutely nothing. So again, you know, same sort of scenario. Somebody got a little suspicious of their platform, so they started running AA tests, and surprise, surprise, got a ton of significant scorecards. The thing that absolutely kills me about this is in the conclusion of this, it wasn't, you know, I should understand hypothesis testing better. The conclusion of this article was, A/B testing is worthless, so just do what you want anyway. And I say that because, like, people's belief in scientific truth and the scientific method is extremely shaky, right? So we have, like, congressmen in the United States who come to the Senate floor and throw snowballs and prove that that means global warming is not there. So, like, you have to be really careful when you build an experimentation platform, because it's very easy for people to lose faith in it. So again, it is important to make sure it works the first time around. So my sense of confusion is then that, like, A/B testing is both simultaneous this thing that Forbes writes about that lifted Facebook and Microsoft and Google to the pinnacle of success and optimization, and at the same time, it's just crap and nobody should do it and it's worthless. So like, how do you deal with these juxtapositions? So I'm going to claim that when you build it, you just need to think about the process and think about your scenario versus reality, and I'll expose some of these unit testing things and we'll dive into the code. So a peek into my bias again, like this short little bias here will show you like really how I think about everything when it comes to experimentation. So I have an analogy where I say reality is to the logs that we view in the same sense that experimental truth is to the scorecard. So there's a reality out there. Someone either likes or doesn't like your site. They like the way it's interacting. They enjoy the features or they don't. And then there's the logs you collect on their behavior, and those are one particular view of that reality. You don't really know what it is, and this is sort of exposing my physicist upbringing, that there's a reality and there's some mathematical construct we have where we view it. Well, that's very much the same in that when I run an experiment, there is a truth. That thing worked or it didn't work. And the point is, the experimentation system should try its best to tell you through a scorecard whether or not you are right or wrong in this outcome. But the point is that they both have their limitations. And designing an experimental system that is aware of its limitations and avoids making the biggest mistakes is one that will serve you very well. If you do one that just gives you answers or tells you the kinds of things you want to know, you're going to be in a little bit of trouble. And my view on that is you can write unit tests that avoid those problems. So where do we start? So I'm going to assume you all have a product and a platform of some kind. If you don't, I don't know, meet up, make a startup, and get one. And I'm just going to add two little complicated boxes to this thing, right? So two complication boxes I'm going to add to this is usually you don't just randomly split users with a script. You have some kind of, especially in large-scale systems, some kind of treatment assignment service. Script, service, whatever you want to call it. But you're going to give a collection of users to this service, or users one at a time, and it is going to return to you what bucket they're in, what treatment they're going to see, right? And this can be a complicated thing. Then on the other side, after you show them the treatment and the control, before I do any stats, I'm actually going to combine these logs, and I'm going to get what I call like this experimental log, this raw log for experiments. And in that aggregation is another point where you can fail catastrophically. So I'm actually just going to concentrate on these two boxes in this use case here, right? So we're going to dig into each one of those boxes. And on the left side, like I said, that's sometimes what you refer to as bucketing. And bucketing can be difficult because random numbers are hard. And we'll explain that in a little bit. And then on the other side, this scorecarding, this aggregation, it can also be difficult because counting and aggregating can also be non-obvious and difficult, and people make mistakes there. So there's lots of talks out there about how people mess up hypothesis testing because they don't understand statistics. But nobody talks about how you can mess up hypothesis testing because somebody wrote a SQL query incorrectly. Right? The same kind of thing can happen. There's just no reason to think that can't happen either. The whole point is that unit testing can help with the latter and sometimes with the former. But I also say it's critical to know that your platform works because users are crazy. They do weird things you don't know. Some of them use a phone that you've never seen before, and it creates an instrumentation bug that you don't know, and then you log it, and you don't know till afterwards, and somebody has to go in by hand and look at it. And so the whole point is any automated test I can write that helps me avoid that is good. So what would a test look like? So this is a mock-up of a test that I wrote and handed off to a dev team when I first got there because they said, I have no idea what you mean by writing unit tests for random data. What does that mean? So I just handed off this mock-up to them, and I said, look, so here might be one of these in your test class. And I said, it just tests the bucket split, that left-hand thing I talked about before. So what is it going to do? Well, it's going to go through every metric in your bucket of important metrics that you care about, email open rate, click-through, whatever your metrics happen to be. And it's just going to ask, are the differences between the two groups you gave me less than some tolerance? Right? This is what it means to test the difference between two random groups. Right? I have two groups. They have some summary of those two groups, and I just want to know that they're close enough that I would consider them the same. Now, canonically, you might think, oh, I want to make sure that it is exactly equal to 0. If you do that, your test will never pass. Congratulations. But again, this last line is a statement of hypothesis testing. Are two things close enough for me to consider them the same? And they thought this was great, and then they realized when they went to implement this that where do I get group A and B? We haven't run an experiment. We can't run an experiment until we have an experimentation platform. How do I go find these things? I don't just want to pull logs from random places for various reasons. So they gave that back to me, and I said, that's a good question. I didn't think about that. In my complicated 3 lines of programs, I didn't think of these two things. So I went away for a little bit, and I came back and I just said, why don't I just make some fake humans for you? So the whole point was there's a lot of pushback because the idea is that, well, this platform needs to serve 10 million people. And it doesn't matter what we do on our current platform, we're never going to get that kind of volume. I said, great, I'll just make some. So if you're a human, this is not very nice to say, but as a data scientist, what do I think human beings are? They're a collection of log lines. So when I look on the logs on my side, everyone who uses my site, they are a group by anonymous ID, get everything they did. So this is actually really good because humans are complicated. Log lines are not. Log lines, when I go to simulate humans, or at least the log lines they would generate, log lines only have a certain range of creative expression. There's tons of things the logs don't tell me about you. They don't tell me the expression on your face when you saw this new feature I put on my site. They didn't tell me whether or not you got stuck in traffic on the way to work this morning so that when you come to work and use my product, you're using it a different way. They don't tell me any of that. They're a reduced amount of expressiveness, which is great because then when I go to simulate them, I only need to simulate that amount of expressiveness. And let's actually see like how we would skip a human and just make a log line. How does a human make a log line? Pretty simple. They visit the site. You don't log people that don't come to your site, usually. When they get to the site, they have a choice. They can do something. They can like a photo. They can post something. They can go to a different page. They can do a search. They can start typing in a search and delete back. You can parameterize all of the things they do into sort of sets of choices, right? And then the whole point is that they have this choice in front of them, and then they make a choice. And then optionally, maybe they make that choice over and over again, depending how complicated your service is, right? Like think of Snapchat. They open the app, they either Snapchat or they don't Snapchat, right? Like there's a few other things you can do in there. But this idea is that they're just making a series of choices. And the whole thing you really need to take away from this is that logs are generated by a process. You actually don't think about this, but this is an assumption you make when you do null hypothesis testing, is that you assume things are generated by a process. And so let's abstract that process a little bit to think about how the computer thinks about it. I think the keynote yesterday was really great because he pointed out that one thing you need to teach children when you teach them how to program is that computers only know what's right in front of them, and they're really dumb, so you have to tell them exactly what's happening. So how does a computer do this process? Easy. You present a choice. What is a choice to a computer? It's a probability distribution. No problem. Probability distribution represents your entire universe. I can do this set of things with this probability, but it defines my entire universe. Then the human makes a choice. That's a draw from that distribution. This is great because these are all things computers can do. We know this. Number 3, given that choice, maybe I'm going to make a new choice. And maybe this time the probability distribution is different, but it's still just another draw. That's great. And after I begin to see that all I'm doing is layering these together, I just have to repeat, which is awesome because this is something computers are unbelievably good at. So if I can do 1, 2, 3, 4, and then I tell the computer repeat, I'm good. So this is actually how you're going to build them, right? It's a simple process, but it really captures the essence of the log generation. So how do I inject some flexibility into this? Well, you can imagine that I can use different probability distributions to represent different kinds of choices. The parameters for those distributions can be different per person, per group, per unit time, per anything, right? And in a very brute force way, you can inject an amazing amount of flexibility into this, right? So let's present a choice and then make it, right? So I apologize, I am definitely like a Python 2.7 person. So if you're still a 2.7 person, you can tweet awesome things at me. If you are upset with my lack of commitment to 3, you can send them to Joel. He would love to hear those. You should also read his book and go to his talk. So what's a choice? Here's a function that does a choice. It's called getBernoulli trial. It has 2 inputs, right? So it has p, that's the probability of success here, and n, the number of times I want you to make that choice. So what's a Bernoulli trial, right? A Bernoulli trial is a coin flip, right? It's something that only has 2 outputs, 0 or 1. And every time you ask it for a 0 or 1, it will give you a 1 with probability p and a 0 with probability 1 minus p. Right? This is a very simple thing. This represents an unbelievably large amount of choices people make when it comes to a weblog, right? So anyone who knows about Bayesian hypothesis testing, right, in the beta binomial model, right, like binomial models are just collections of those things, right? So this is a very simple choice. So I can do this. It does work, right? If I have a collection of 10,000 people or one person that visits 10,000 times because they're really into your product, here's them making 10,000 of those decisions, and of course, as we might expect, if I expect them, half of them to be right and half of them to half of the time he takes that, half of the time he doesn't take that, then I actually get that right. So this is nice, but not all things are that simple. But math bails us out here. There are lots of probability distributions that describe lots of processes, and then your task is to map those processes to things you think humans do. Right, so I can have, in the top one there, I have a draw from a beta distribution. That can help me create different probabilities for those Bernoulli trials that create diversity amongst people's decision making. I can use an exponential one to create a population of people where most people do very little and a small number of people do a lot. That's your typical search engine, actually. You can get an experimental result. I can do a ton of Bernoulli trials all in a row. That ends up giving me a binomial distribution, right? So the distribution of successes for a number of these individual Bernoulli trials as a binomial distribution. And then maybe my users have different visit frequencies. Maybe someone's a constant Facebook checker. Maybe someone only checks it once a month. That's great. I can use a Poisson distribution to tell me about those users, to give me all of these things. So the whole point is I can take these things and tie them together and make a fake log. So let's just make a quick one. And then we'll understand how we're going to use this, right? So how do I make a clickstream log? Easy. I imagine somebody comes to my site. This can be a probability. They don't have to always visit. They can execute a Bernoulli trial. This is them clicking, right? So think of an email offer or something like that. So they come to the site, they either click on the offer or don't. That's going to send them to a landing page where they either buy or they don't. That's just 2 Bernoulli trials back to back. So that represents almost most of your email campaigns, I'm assuming. So all I do is just make those 2 choices, and then I'm going to log that and make it look like a log so that I can test things like data ingestion, data handling, all of this kinds of stuff, data processing times. So let's actually do that. I have this function here called generate impression, right? So it's pretty simple. It takes in these 3 probabilities: the probability that you will come to the site, the probability that you will click, and the probability that you will buy something, right? Now I'm abstracting the user behavior a lot, but remember, your logs do this already anyway. So what do? I get an impression, right? That's just a Bernoulli trial with impression. Here I'm cheating a bit because I'm guaranteeing that they come to the site. Usually don't log people that don't come. If they did visit, just ask me if they clicked. No problem. If they did click, just ask me whether or not they converted. No problem. If they didn't click, I'm going to say they didn't convert. Optionally, people often buy things not through your offer. I can just make that another Bernoulli trial with a different probability where I think they have maybe a lower probability of buying because it's not on sale or they didn't do something. The whole point is just with these 3 Bernoulli trials, you've already injected an amazing amount of accuracy into what email offer generally looks like. And then I'm just going to return this impression, right? So what do I see? Well, I see, what do I get? I get these 3 numbers, right? Did they click, did they convert, and did they have an impression? This is good, but it doesn't look like a log yet. So I'm going to generate a log line where I stick a random timestamp and a random user ID there, right? So my friend Trey, he's going to come to my site, and same thing happens before. I generate the impression, take some random time, add some random time delta to it, add it on here, smash them all together, and output this line. This is great. It's not quite there yet, though, because nobody stores usernames in plain text unless you're Time Warner Cable. And so let's hash that, right? So that's not so bad. I'm going to SHA-1 hash that. That's not a big deal. So I'm just going to turn this into a data frame now so we have something that looks kind of like a log. I'm going to take Trey. I'm going to hash his ID with the salt Spurs always let you down. So if there's any Tottenham Hotspur fans here, I apologize. And then I'm just going to make 10 log lines for Trey, and that's what it looks like. This is really starting to look like a log. I did 3 Bernoulli trials, 3 draws from 1 distribution. It's about 20 lines of code. But I've made something that looks like the aggregated output of an email offer log. So this is how email campaigns work. And in fact, you can generate these and do nice things like send these to people and say this is the output of your experiment and just see how much they actually believe it. Because it turns out it's quite the dead ringer. So this is good. I have this kind of thing, right? But you can do more with this, right? Think of the formula. The formula is really simple. Encapsulate a human behavior you care about into a probability distribution. There is a lot of knowledge that goes into this, right, though? But if you're trying to model the number of times distinct events happens, you have a distribution for that. It's Poisson. The time between those events, it's an exponential distribution. Binomial for total wins or total clicks, total purchases, total something amongst a population of people. The beta distribution is amazing because it allows you to inject diversity into all of these probabilities that you have here. And then normal because it's popular and everybody wants to use it anyway, but you don't make heavy use of it here. But you chain these distributions together to form an impression, a user impression, and then you vary the parameters either within the chain, across users, across populations to generate diversity. So it's very easy to make controlled, random distributions of users that have particular consistent behaviors. And it looks a lot like the behaviors you had before, right? So the simplicity is deceptive. But one thing you need to realize is that this is actually just Bayesian statistical testing backwards. Right? Because what do you do there? In Bayesian statistical testing, you assume the log was generated by some kind of process, and your point is to recover the parameters of those distributions and compare the parameters to each other between treatment and control and ask if they're different. Well, what's wrong with just doing that backwards? In backwards, I inject the parameters, generate the logs, and then I want to measure them backwards. Again, so that is the big assumption, right? The model assumption here is that these do obey these distributions, right? But you're making that assumption anyway when you perform the statistical test. So now what does the test look like, right? The test is extract the unknown parameters. This is how you write unit tests. You make fake logs that have parameterizations, probabilities of clicks, number of users, things like this, and you ask your experimentation system to faithfully recover those. If it can do that, you put a known input into the front of your black box, and you got the correct output on the other side. You know your system is working, independent of people who have weird, wacky behavior that you can't control. And that's what they are, right? Simulated logs are nothing more than noisy instantiations of your supplied parameters. Just recover those parameters. This is how you test random data. So Justin did a great tutorial yesterday, and there's a lot of questions coming up about like, how do you test the output of simulations and random variables? You try and recover the parameters that generated those random distributions. And so I say your task, well, the dev's task, let's be honest, who's doing the real work here, is to recover those parameters within reason. So let's revisit that AA test, and let's write some actual unit tests in our last 15 minutes here, or 10 minutes here. So I'm going to return to that AA unit test from before, the test bucket split. And I want to be just very explicit about why this is important, because most people don't pay attention to this, and it's the reason all of those blog posts are going up. So when I have my users and I randomly split them into two groups, they haven't actually become treatment and control yet, right? I haven't shown them anything different. They're just two groups of people. And in fact, to the left of t equals 0, where I show them treatment and control, they had better be the same. Right? This is the place where they're better be the same. This is an implicit assumption of your hypothesis test, that they are the same. On the right side, they're allowed to be different, because one of them has seen your awesome change and the other one has not. So we better make sure they are the same before. So let's refactor that AA test just to be a little bit more friendly to what we have here. So now I'm going to take this bucket split test, and I'm going to give it two data frames. One of them is the control group. One of them is the to-be treatment group. And then I'm going to give them a metric. And I'm simply going to ask, is the p-value of the difference between those two groups significant or not? Right? So before, when I said, is the difference less than some tolerance level, that's really what you mean when you're asking this here, right? So I'm just going to say, when I get the p-value of comparing these two groups, either through a t-test or a z-test or your favorite awesome test, it's always going to be a t-test, between these two groups for this metric, is it greater than 0.05? Meaning, to my knowledge, to the best of my ability, can I not tell the difference between these groups? That is what equivalent means in this sense. So let's do that. I have some parameters here. Click control. Click convert users and rows. I'm being a little hand wavy because I don't want to go through too much of this, but I have another function called simulate log vectorize, which will do what I talked about before. Inject diversity into people by changing the parameters and generate a bunch of logs that look like the same one I generated for Trey, but have many users with diverse behaviors. But the important thing to realize is that when I do this, it's the same probability for both groups, right? It's the same parameters for both groups. So A and B should not be different. They might be slightly different, because that any random draw is going to be different than any other random draw, but as a collection, they should not be different. I generated them with the same parameters, right? And just to give you an idea, like they look like this, right? So they just have different user IDs, the times are a little bit different, all of these kinds of things, but they're just the click logs that you saw before. So now I want you to sort of ask yourself, will that unit test pass? Like, commit to an answer in your head. This is the fun part. So if I generated two things with the exact same parameters and I compared them to each other, is that unit test going to pass or not? It does pass. This is good. No assertion error. This is good. This is what we should see, right? I should not see a difference between these two groups. This is really good. The point is, though, is this always true? So if this is passing, like, why am I so wary of random number generators, right? Why do I need to confirm that a random split is really a random split? Well, when I think about randomly splitting users, this is like my most Reagan-esque moment in my life, because I do trust random number generators, but I always verify them. Because the whole point here is that random is random except when it's not. So let's make it real. Most of the time, you don't only have one metric that you care about, right? You have maybe many metrics that you care about. And in this case, I'm just going to write a function here, add metrics, that just adds a Bernoulli trial column onto each one of those data frames. So that's just a way for me to add additional metrics that might be like that p-click metric, right? So this is just going to take it and get a number of Bernoulli trials and just slap that onto the end of the data frame. And then I'm going to write another function called the AA failotron. And what it will do is just add those metrics onto the groups. And then it's just going to, for every metric that you added, perform this test again. Right? This is actually something very common that you see, right? Someone makes an experimentation platform that you saw before. They add metrics as they become important to their product, and they start outputting them in scorecards. So now the question is, the name of the function is a little bit foreshadowing, but in this range, I'm going to perform this test bucket split n metrics times. Will that assertion ever fail? Will I ever get an assertion error? Right? I generated them by the exact same process I generated the click column from before. There's nothing different about it, because the probabilities between the two are the same, right? Identical columns. The point is, it does fail, right? And so this is something that Martin, who did a PyData talk, I think 2014, talked about quite a bit. This is the multiple testing problem. And most people, when they build an experimentation system, do not think about this and just willy-nilly add metrics as you go. So what's happening here, right? Well, why is this failing? Well, eventually at one point I got a p-value that was less than 0.05. So my randomly split, identically generated groups were not identical. But that's actually not surprising, because the whole point is that every time I test a metric, I'm accepting this 0.05 probability of a type 1 error. And the whole point is, as I add additional metrics, I'm testing over and over and over again, the family-wise error rate, the error rate that I might say type 1 error rate for the whole family of 10 tests, goes above that number. So I will fail. I'm guaranteed to fail at some point. So this is good, because I did this before I made a decision based on this, before I got a scorecard back that erroneously reported the outcome because I didn't correctly split my users into two groups. So I can actually write a function called countDemFails, which does the same thing, but instead of an assertion, it just takes the p-value and counts the number of times it would have failed, right? So you can see that if I have two metrics, I only added two metrics. I'm only testing two metrics. That in the course of creating 10 experiments or 10 splits per experiment, I do actually fail one time. One of those experiments would have been invalid because the two groups created by random chance are not identical. If I up it to measuring 5 metrics, I know that seems like a lot, but email open rate, email click-through rate, email unsubscribe rate, email subscribe rate, and then conversion. There's 5 metrics for one email test. It's not that hard to come up with them. And trust me, once you do an experimentation, people love to add metrics. So here's the second one. It failed 4 times. 40% of my experiments that I ran in that sequence of 10 had incorrect splits in the beginning. By the time I get to 20 metrics, I'm almost guaranteed to fail. But that's OK. We can correct for this, or Bonferroni can correct for this. So there's an overcorrection called the Bonferroni correction, where I just require that family-wise error rate, the whole 10 metrics error rate, actually matches what I originally want, the 0.05. And I do that by just saying, every individual test, I have a stricter requirement for what equal means. The p-value needs to be smaller than that. And this is a brute force way to do that. This is great. I redefine these things to take in n metrics now, and instead of comparing it to 0.05, I convert it to the Bonferroni correction. And I get this, it doesn't fail, and it passes a lot. Great. I've added something to my code that now does a correction on the p-values, and I've corrected for multiple testing before I've ever made a mistake. Just by witnessing this, congratulations, you're better than 80% of the experimentation platforms out there. Most of the big ones correct for this, don't worry about that. But a lot of the implementations you see just have no mention of this. And you already corrected it before you even ran an experiment. This is good, but here's another question. Will this fail? Can I make this fail? I just introduced a correction that should correct for this, but is it possible for this to fail? The answer is certainly yes. If I did this 100 times, I will fail. It's still guaranteed. The family-wise error rate is down to 0.05, but if I do 100 experiments, one of them is guaranteed to fail. You expect one of them to fail. It's not guaranteed. Expectation, yeah. The expected value is that one will fail. It's OK, though. This is expected. This is expected. The whole point is your platform should know this. In AA, you always verify that it doesn't fail. What does that mean? It means you re-randomize your groups until they pass. So anytime you kick off an experiment, you don't accept the family-wise error rate that you might have. Instead, you shuffle them, check the AA. If they pass, you proceed with the experiment. If when you shuffle them, they fail the AA, doesn't matter. Grab a new salt, reshuffle them, you will pass. Then you send them into the experiment. So you, just by witnessing the failure of your tests and simulated logs, can correct for this. And like I said, most experimentation platforms don't correct for this as it is. This is the multiple testing problem you've seen. So just quickly on aggregation, right? So that's one way to avoid failures in AA testing. Those 2 blog posts I showed you before, they were entirely, I don't work at those companies, but from reading them and understanding what you see, they were having AA failures, right? So they were running tests just assuming, resigning themselves to the idea that you will have this 0.05% AA failure rate, and you're just going to take it because it's a small amount of tests. Again, when you work on a platform that runs thousands a week, and users are in multiple experiments, and you have interactions between experiments, failing one of them is not OK. It ruins other experiments. You have to be conscious of that kind of thing. So that's one way to fix it. Congratulations. OK, so now onto the right-hand side of that thing, aggregating, right? So how do I aggregate before hitting things with a stat stick, right? So I'm just going to ask you all a question. How do I calculate, just from that simple log, no 10 metrics, no anything, just that click log, how do I calculate the average page click rate per user? Just think in your head, talk to your neighbor, pull out something, write pandas code, whatever you want. I want to calculate this, the average click rate per user. A lot of times what you see in scorecard things is this. Take the data frame, take the click column, and I take the mean. You ask me for the average click-through rate. Don't do that. That's okay. A lot of things are like that. That's one measure, but don't do that. Why should you not do that? When you think about real logs are made of collections of users. A lot of times it's not a bad generalization to say that you have a small amount of users that generate a lot of your traffic, and then you have a large amount of users that generate a moderate amount of traffic. If anyone's ever heard of the 80-20 rule, that's the instantiation of this, right? Some small amount generate a lot of your traffic. That's great. So I'm going to make a data frame that has those two things, right? So I have 10 users that generate 50,000 impressions over some amount of time, and they're super clicky. They click on everything. They're probably bots, but that's okay. That's okay. We won't tell that to our investors. Then I have 1,000 users, and they only generate 10,000 rows, right? So they are a minority of the rows, but they are a majority of the users. And they are much less clicky. So when I do that first thing, that click mean, what do I get? It tells me that the average page click rate, right, because every impression is a page view, average page click rate is 0.68. That is not accurate. Think about that. That's a summary statistic of that distribution. You know when you generated that most people have a 0.1. I have a 10% click-through rate. So when I give you a summary statistic that says 68% of the time people will click, that is an inaccurate summary of what's happening. It's one thing, but for your desire in the experimentation is to understand what's happening to the user. That's a misleading assessment of the user. Instead, you should do this thing called double averaging, right? So for every user, I group by the user and I find their page click rate. And then I average across all of those. So what is this doing? This is a weighting thing. The first one is a weighted average, where the people who generate most of your traffic are weighted more than the people who are not generating most of your traffic. The second one is where everybody has weight 1. I have removed that user difference between everybody. And there you see the user level click average is 0.1. And that's much better, right? Because if I dip into these users, what am I going to do? Well, overwhelmingly, I'm going to grab people from the not so engaged bucket, and their click-through rate is going to be 10%, and that's great because that's exactly what I see. So why is this important? Let's say your experiment has a lift of 10%, right, in CTR for your heavy users. So that's easy. I just take those heavy users, increase their click-through rate by 8%. And then what do I see on the other side? Well, the impression level click average has shot up. And we should expect that. It's overly sensitive to these users. But the user level one hasn't really moved that much because you haven't changed that much of users. And then this click report is just a way to do a quick sort of experiment about that. And the idea is that, yes, the impression level one measures what you input. But this is an incorrect effect size. If I release this change to everybody, I've changed 1% of my users. So to say that this experiment will lift 10% of your user behavior is an inaccurate result, an inaccurate assessment, but that's what people will read out of the scorecard. Instead, I will get a lift. I did move people's behavior, but the effect size is actually much smaller. This thing called average treatment effect is actually much smaller than you look at. It works the other way too. If 10% of my light users exhibited a 10% lift, what do I see? There I'm just adding a little 10% lift on 10% of those users. The impression level average is completely insensitive to this. It can't see it at all, because they're a minority of those things. You didn't move the weighted average at all, but the user level one does detect the move. So the point is it's just as valuable to say them, right? So you want to make sure to write unit tests that understand the sensitivity of your experimental platform, that it doesn't make incorrect decisions based on these kinds of things, right? So you can have a test like this, correct rollup. You can give it this test case I had before where your heavy users, which are a small minority, have a huge lift, and you just want to make sure that the user lift is less than the impression lift. If your scorecard can communicate that to you, it's doing the correct thing. It will stop you from making mistakes. So what are some things we should think about as I conclude here, right? Unit testing is common ground, right? It's the way non-hardcore developers can communicate with developers. I write a test, the passes of which will create a robust and useful experimentation platform. If it passes, great. Log simulation is actually surprisingly accurate. So using these logs, I simulated a month of behavior for various summary statistics on Bing, and you're within 6 decimal places of the exact thing, right? So users aren't as complicated as you might think. The last one, or the third one, is like a fear-mongering thing. Mistakes can exist in your platform at tons of places, and you should be very careful to guard yourself against those. So that's like my fear-mongering part of that. I don't want to make people think that it's impossible to make one that works, but there are mistakes that go everywhere. And the last one, this is just really true. Like, users are weird. Human beings make weird decisions. Sometimes your campaign doesn't work because there was a rainstorm in the northeast of the United States and a bunch of people's cars broke down, so they couldn't receive your email to go redeem the offer because they were at somewhere getting their car towed out of a river. And your logs have zero knowledge of that. There's no way for you to know that. So you need to make sure that your experimentation platform is telling you the correct things and not erroneously leading you down some paths. And with that, I'll just leave this up here at the end, and thank you for your attention.